Okay, welcome to week 2, part 2. We left off on Monday here at slide 22, illustrating the idea of multiplying a vector by a supposed scalar. Actually, this is multiplying a vector times a vector of one item. And in this case, what happens is that one item gets stretched out to 3 items, the same number of items as are in the vector, the vector v2 in this case. And so we end up with an item by item multiplication giving us 3, 9, 15, since v2 contains these 3 items, 1, 3, and 5. Now I have corrected one of my many, I guess I had Python on the brain or something, mistakes where I had equal signs instead of the gets operator. Well, so let's press on. And okay, now the default indexes for the items within a vector are just 1 through n, where n is the number of items. But you can, if you wish, provide names for use as the indexes for the items within the vector. Here I've typed those in double quotes. Let me pull up my RStudio. Here we go. Okay, so I have relaunched RStudio, and I have typed in all of the code up to what we needed up through slide 22, so I have the same variables that I should have. And here I'm saying v7 gets, okay, I'm too lazy to type that in, so let me copy and paste it. Okay, so here I'm using the combine function, C, and I'm creating a vector of 3 numeric values, double values, but I'm giving them names, A, B, and C. So v7 now is a vector of 3 numeric values. If I ask for the type of v7, I get told those are doubles. But this vector has names associated with those items. And I can access the items either using integer subscripts as I usually do, so v7 sub 2 gives me the 7, or I can say v7 sub b, if I could type. There we go. So that's how I do that. Now, actually, when you create a vector and you give names, you don't need to use the quotes. So I could have created this vector v7 by just saying A gets 5, B gets 7, C gets 11. That works just fine. But then if I attempt to access v7 sub b without the quotes, I get an error. Now, actually, if the reason that I'm getting this particular error, I'm getting this not available error, NA, is because I happen to have a variable up here whose name is B. Well, in fact, we can see the definition of B up here. So when I say v7 sub b, I'm actually trying to access v7 sub 123, which doesn't exist. Okay, let me remove, okay, I haven't shown you this, but very likely you know. Maybe I did show you, I forgot. You can get rid of variables that you don't need anymore by removing them. This is another appropriated Unix command, actually. And so now you'll see in my global environment that the B variable has been eliminated from the list. And now if I access v7 sub b, I just get an error message saying there is no such thing as B, and I have to remember to use the double quotes to name the B item within the vector v7. Okay, So, it's up to you whether you use the quotes when you define the vector, and maybe that makes it easier for you to remember to use the double quotes when you access the item within the vector. Or you can leave the quotes out, but you're still going to have to remember to use the quotes when you try to access a value. Now, v2 is a vector that already exists, contains these integer values 1, 2, and 3. If I already have a vector that does not have names associated with it, if I say, for example, names for v2, I just get null. But I can define names for v2 by assigning a vector of names. So let me just call these x, y, and z. And here, because this is a vector of strings, a vector of character types, I do have to use the quotes when I define the names this way. What did I do wrong? Oh, typo, sorry. Okay, that should be names, of course. All right, and so now I have added names for v2, and I can therefore use those names as subscripts into v2. Okay. All right, well, I've basically already shown you all right, formerly names for v2 were non-existent, null, and now I have added names for v7, a, b, and c. Adding names to this vector does not get rid of my ability to use integers as subscripts, or sequences of integers as subscripts, or Boolean vectors as subscripts. I can still do all of those things. It's just that now I have the ability to use these named subscripts, these named names as well. So for v7, as we've seen, I can say v7 sub 1 to get the first item. I can say v7 sub 2:3 to get the second and third items. I can say v7 sub, let's say, true, true, false to get the first two items. I can say, actually, v7 sub, and then give a vector of names. And in this case, I do have the option of changing the order around. Okay? So I've increased the variety of ways that I can access items within this vector. Now, all of the items in a vector have to have the same data type. What happens if you do try to create a vector where the data types don't match? What if I say v8 gets a combination of, 1L, not IL, and 2. So maybe I accidentally just left out the L after the 2, but the upshot here is that I have the integer value 1 and the double value 2 that I want to combine together and put into v8. Should I get an error message? Well, I don't. Interesting. What happens is that R notices that you're creating a vector, that you're combining together mixed data types, and so what happens is that all the values are coerced to whatever the most general or most complicated, if you will, data type is among those values. And in this case, because I have an integer and a double, the integer gets coerced or changed or converted into a double. And so what I actually have here in v8 is a vector of two doubles. And in fact, if I ask what is the type of specifically V8 sub 1, I get told, okay, that thing is a double. In this next example here for V9, if I say V9 gets a string and a double and an int, well, in this case, R decides, well, the string is the most general one of these. I know how to convert a double to a string, and I know how to convert an integer to a string. So everything ends up getting converted to strings. So type of V9 is character. It's either a feature or a bug, depending on your point of view, that R doesn't warn you that it's doing this. And also, I guess I just want to point out generally that when one of these coercions, when one of these type conversions occurs, not only do you not get any warning or error about that, but there's also no way of undoing it, okay, other than to just start over again. Okay. So here on slide 28, we're going to create V10, which is a vector of doubles. Okay, let me get that in there. Okay, so V10, whoops, V10, not V1, V10. All right, I'll get this right. V10. There we go. So V10 is my vector of 4 double values. I can convert to some other data type by using one of the so-called as functions. This is an explicit type coercion as opposed to the implicit one that occurred in the previous examples. So if I say V10I gets as integer the items in V10, R is going to convert these double precision values, these floating point values, into integer values. And the rule that R follows is the same one that is used in C and C++ and Java. That is that the fraction part is simply chopped off. And so V10I now contains the the integer values, the long int values in the machine, 1, 3, 5, and 7. Or if I wanted to convert these things to strings, character strings, I could say as character V10. And now I have those things represented as strings. Numbers, it turns out, can be converted to logical values. So here's V10. And if I say V10, whoops, if I say as logical V10, this works fine. It turns out the rule in the rule in R, it's the same as the rule in Python and C and Java and elsewhere. The rule in R is that zeros are false and any numeric values other than 0 are true. All right, so these values, 1.2, 3.4, 5.6, 7.8, convert to logicals as true. If I were to say as logical the value 0, well, let me create a combination of the integer value 0 and the floating point value 0.0. Now, I could just type plain old 0 there for floating point, but I'll add the 0.0 to be really, really clear. These are both interpreted as false. Strings, on the other hand, as illustrated here on slide 28, in R are not convertible to logicals. So if I try to convert V10s to logicals, NA here is the token that stands for not applicable or not available. It's what's used in R to represent missing or invalid data. Okay, so we use as integer, as character, as numeric, as double to convert items in a vector, or for that matter, items in any data containing object, into the type that we request. We can test whether the type is numeric or integer or what have you using one of the equivalent or corresponding is functions. Okay, so here's my v10 array vector, excuse me. Okay, and if I ask whether is double v10, that is true. Remember that all the items in a vector are going to have the same data type, and so in this case every item in v10 is double. I can also ask, or if I ask, I should say, whether v10 is integer, that's false. But if I ask whether v10i is integer, that's true. Now, numeric is, in some sense, in terms of this test function, a sort of broader category than just the numeric data type. If I ask whether is numeric either v10 or v10i, both integers and doubles are categorized as numeric, so it's true for both of those cases. And if I ask whether is character v10s, that is true. Okay, so as a reminder, v10 was our doubles, v10i was our integers, and v10s was our strings. All right, well, that takes care of vectors, or at least what we're going to talk about. We could drone on and on. Next, we're going to take a look at the list collection type, or data structure. A list can have items in it that do have different types. Here I'm creating a list called n, and within n I'm going to put an integer 5, a double precision 4.2, and a character string high. And unlike a vector, that works fine, and the list keeps those items separate from each other. Now, of course, we know that R does not really have scalars, so although I typed one int value, one double value, and one character string value, those are actually one value wide vectors. So the first item in the list n is a vector of one integer. The second item in the list n is a vector of one double. And the third item in the list n is a vector of one string. On my list n, I can use the subscript notation, the square brackets, to access a particular sublist of this list of 3 vectors. So if I say n sub 1, let's say, remember what I have here is a list of 3 items, a list of 3 vectors. N sub 1 is still going to be a list. It's just a list of 1 vector instead of a list of 3 vectors. N sub 2 is also a list of 1 vector. In this case, it's a list of the 1 vector containing the 1 double value 4.2. To access the contents of a particular list item, you use the double square bracket notation. So whereas n sub 1 gave me a list containing one vector, n sub 1 gives me that vector, and n sub 2 gives me the vector currently containing the one double value 4.2. It's very easy to get confused between the single set of square brackets, which gives you a list of vectors, in this case just a list of one vector, versus the double square brackets, which gets you the vector contained within the list. All right, so here on slide 33, we're going to create a new list called N2, and this list is going to contain a couple of vectors that are longer than just one item. So I'm going to have a vector of int values, 2L, 3L, 5L, 7L, 11L. Those look suspiciously like prime numbers. And I'm also going to have another vector of 2 values. Now, this plus symbol that's displayed here is what's called the continuation prompt. It's R's way of telling me that I have not finished typing a full statement yet. All right, so this is going to be 3.14159 and 71828. So E and pi to not very many decimal places. All right, and so now N2 is a list of 2 items, and each of those items is a vector. If I ask for the type of N2, I get told, all right, N2 is a list. If I then request the sub 1 item, N2 double sub 1 of N2, that's going to be the vector of 5 int values. N2 double sub 1 is a vector, and therefore I can subscript within that vector in the usual way by saying sub 3. So that vector sub 3 should give me the 5, and it does. Okay. Now, N2 sub 1, without using the double square brackets, gives me a list containing that vector of 5 integers. N2 sub 1 does not give me the 2. All right, I might hope that N2 sub 1 is going to give me the 2, the first item within that vector, but actually no. N2 sub 1 is still a list. It's just a list of the first. It's basically a sublist of N2. It's a sublist containing a list of one vector. And so N2 sub 1 is actually saying, give me the first sublist from the first sublist of N2, and it's the same thing as N2 sub 1 itself. Okay, so you start with a list, and if you use the single square brackets and a subscript, you get a sublist. It's still a list, it just doesn't contain as many vectors as the original list. So in this case, N2 sub 1, instead of being a list of 2 vectors, is a list of 1 vector. And if I say N2 sub 1, I'm asking for the list of 1 vector from within that list of 1 vector, which is just the same thing as I had. Okay, so you know, don't get confused about the distinction here between the single square brackets, which returns to a list, versus the double square brackets, which returns to you an item from the list, which is to say a vector. All right. Now, if I display v6, did I forget to create v6? Apparently I did. All right, so let me create v6 now. v6 gets 3, 9, 15. I think that was created by multiplying 1, 3, 5 by 3. So let me do it that way. v6. All right, so there's v6. I can, as we've seen, use type of to discover the type of value within v6, and I can use length to find out how long v6 is. I can also use this nice function stir to print out a summary of a bunch of information all at once. I'm told when I ask for the stir of v6 that this thing is a numeric vector, that it contains 3 elements, item sub 1, 2, and 3, and that those values are 3, 9, and 15. Now, if I had a vector that was very long, I wouldn't necessarily see the whole thing. I'd probably just see a subsection of it. v7 is a vector to which we added some names. And so if I ask for the stir representation of v7, not only do I get told that this is a numeric vector of 3 values, and those values are 5, 7, and 11, but I also get told that this is a named vector, and here are the names. The names is a vector of character strings, A, B, and C. So as our data structures get more and more complicated, stir is going to be handy for showing us a nice descriptive summary of those data structures. If I ask for, let's just display N2 again in list form, all right? So that's a little bulky on the one hand, and it's also missing some information that we might be interested in on the other hand. So if I ask to see stir of N2, I get told, okay, this thing is a list of 2 vectors. The first vector is a vector of int values, and there are 5 of them. And the second vector in the list is a vector of num values, numeric values, double values in our case, 3.14 and 2.72. Now, just as we can name items in a vector, we can also name items in a list as well. If I say names of N2, rats, I've got an equal sign here again. I missed that one. All right. So name sub 2 gets, I'll use prime as my first name and trans, because transcendental is much too long to type, as my second name. And now I've got the first vector here. This vector of prime numbers is named prime and is still an int vector. And the second one of transcendental numbers, very, very brief representations of supposedly transcendental numbers, is called trans. Now, I can use N2 sub 1 to access the sub 1 vector from N2, or I can say N2 sub prime to access that same vector. If I wish to provide names for the items within one of these vectors, I can do that as well. I can say names sub, let me provide names for these transcendental numbers, N2 sub trans, double sub actually. Names is a function. I should be using parentheses here. Oh, what happened? Okay. All right, so RStudio tries to do you favors by throwing in matched parentheses or matched square brackets, and of course sometimes that, if you have made a typing mistake, then RStudio just makes your typing mistake worse. All right, so n2 sub trans is the vector of transcendental numbers, and to that vector I want to store names of pi and e. All right. So now when I display the stir of R2, okay, I see that this is a list of two vectors. The first one is called prime. Well, it's a list of two items. In this case, they happen to be vectors. We also can have lists of lists, or lists of lists of lists, or lists of data frames, or lists of all kinds of other things. But this is a list of two vectors. The first vector is named prime, and is a vector of int values, integer values. The second vector is named trans, and it is a named vector of numeric, that is double values, and the specific names of those two values are pi and e. So now I can say n2 double sub trans to access the transcendental numbers vector, and from within that vector I can access the value of e, and there we are. Okay, so notice, by the way, that I typed out 5 digits after the decimal point, but stir is just trying to print for you a reasonable representation of what's going on, and so stir by default chooses to round those things off to 2 digits. Now, as opposed to saying n2 double sub trans to access that vector of transcendental numbers, an alternate notation that R allows me to use is the $ followed by the name of the list item. So I can say n2 $, and I don't have to use quotes around trans in this case. All right, so that's simply a briefer alternate notation for saying n2 double sub with the name trans. And I can subscript into that vector then in the usual way. Since I've named that particular value e, I can access it by using sub e. Or I can, of course, use the index, the numerical index. Alrighty. So you can have lists of anything. I've created lists of vectors to illustrate, because basically when we get to data frames, a data frame is going to contain a list mostly of vectors. But you can also have lists of lists, lists of lists of lists. You can have lists of just about any kind of thing. All right, so that's now sort of the difference between vectors and lists. Vectors have items that all have the same data type. Lists have items that have potentially different data types from each other. And we have different notations for accessing items within a vector versus items within a list. A matrix is basically a two-dimensional vector. And like a vector, all of the items in the matrix have to be the same data type. One way of creating a matrix is to use the matrix function, and so that's what we're doing here with this example on slide 41. Well, let me just build up to it. So if I say 1:12, of course, that gives me the sequence of integer values, from 1 up to including 12. And I can create a matrix from those values by specifying how many rows I want and how many columns I want. If I could type, here we go. All right. So now I have this matrix M, which has 3 rows and 4 columns. People typically do name the arguments by providing the parameter names, but the rows and the columns are always specified in that order. So you can get away without typing that n row and n col. You can just say 1 colon 12, 3, 4, and that works the same way. And within the matrix, I can use the expected kind of row and column subscripting. I can say m sub 1 sub 1, 1 comma 1, excuse me, to access row 1, column 1, m sub 3 comma 1 gives me row 3, column 1, and so forth. Notice in the display that the column representations here are comma 1, comma 2, comma 3, and the row representations are 1, comma 2, comma 3, comma. Those are actually usable subscripts. So if I say m sub 1 comma, that actually gets me the entire first row, and m sub comma 2 gives me the entire second column. All right, I'm getting a little ahead of myself here. Let's catch up. Now, it may surprise you, or it may not, depending on how much you know R and how much you know other languages, C, C++, Java, and so on, that the values of this vector 1 to 12 get stored into the matrix in column major order. That is, the first column is 1, 2, 3, the second column is 4, 5, 6, the third column is 7, 8, 9, and the fourth is 10, 11, 12. If that's not what you were expecting, if you were expecting the first row to be 1, 2, 3, 4, and the next row to be 5, 6, 7, 8, and so on, you can reorganize things by changing or by creating a new matrix, which is the transpose of the original matrix. Now so that actually doesn't do what I described. I was saying perhaps you wanted 1, 2, 3, 4 in the first row, 4, 5, 6, 7, 5, 6, 7, 8 in the second row, and so forth. To do that, what I would do is something like this. MT2 gets the transpose of the matrix 1 to 12, where n row is 4, 4, and n col is 3. Okay, so I'm going to get a matrix of 12 values, 4 rows, 3 columns. So those are going to be plugged in row major order, column major order. So the first column is going to be 1, 2, 3, 4. The second column is going to be 5, 6, 7, 8. The third column is going to be 9, 10, 11, 12. And when I transpose that, come on, MT2, I do get the list that I was, the matrix that I was describing with 1, 2, 3, 4 in the first row and so on. All right, so you may discover that this is useful to create the matrix knowing that it's using this column major ordering, and then transpose it to get the format that you prefer. Okay. Well, I've already shown some of these examples, but let's take another look. So here's MT, my transposed copy of M. MT sub 2 comma 2 is the 5 here, second row, second column. MT 1 comma sub 1 comma is the first row. M sub comma 3 is the third column. Notice that the rows and the columns, well, in fact, everything, of course, everything is represented as a vector. So the third column is not represented to me in column form. It's just the vector of values extracted from oh, I had a heart attack for a moment there. I was thinking, wait a minute, I should be getting 3, 6, 9, 12. Of course, I would get 3, 6, 9, 12, except I accidentally referenced M instead of MT. So MT sub comma 3 gives me what I was expecting to see, 3, 6, 9, 12. Okay. All right. Now, you can also use index sequences. All right, so MT sub 1:2, comma, that's going to be rows 1 and 2 and all columns. All right, so that's going to give me, well, wait, here's MT. So that's going to give me rows 1 and 2, all the columns of rows 1 and 2. And here I'm getting rows 2 and 4, columns 1 and 2. So this is grabbing just a certain slice. Okay, this particular slice out of MT. And I can use logical selection. Although there's a special feature about this example here. So maybe I should show MT again, just so that it's right at the bottom of our screen, and then MT sub, and I'm going to create a vector of logicals, booleans. Now, oops, I'm missing my comma. So MT is my matrix. It has 4 rows and 3 columns, and I have specified a logical vector of 2 values for my rows. Now, it turns out that when there are more rows available in the object that you're accessing, then you have logical values in your vector that's making selections. What R will do is to pad out that vector to make it the correct length, assuming that the length of the selection vector is an even multiple, or an even divisor, of the number of rows in this case. So what I'm actually getting here is the same as if I had said MT sub C true, false, true, false. Okay, since there are 4 rows, but I've only given a vector of 2 logicals, those 2 logicals get repeated again in the same order. Forgot my comma. Okay. Yay. Okay. And the 2 logicals get repeated again in the same order, so that there are the same number of logicals as there are rows in this case. Alrighty. You can modify an item in a matrix by just assigning a new value to it. So here's M, the original matrix that I started out with, and if I say M sub 2, 3 gets minus 7L. Now this is a matrix of integers. I guess I haven't proven that, but I did create it using the sequence of integers 1 through 12. Let me show that the type of all of the elements in M is integer. Okay, so a matrix has values that are all the same data type, just like a vector does. And if I say m sub 2 comma 3 gets minus 7L, type some stray quotes there, sorry. Now I have a 7 in, come on now, I have a minus 7 in row 2, column 3. And I have not, everything in here is still integers. So that changed a single value. This next example is showing how you can change an entire row if you wish. You just have to make sure that there are the same number of items in the row that you're changing as there currently are in that row in the matrix. So let's, as a reminder, notice that the sequence starting from 8L, going down to 2L, in steps of minus 2L, that produces a vector of 4 integer values, 8, 6, 4, 2. Consequently, if I say m sub 1 comma gets that sequence, and let me copy and paste. Oh, here we go. Cool. I'll just put my m sub 1 comma in front of that. There we go. So if I say m sub 1 comma gets that sequence, since that is the correct length, I completely replace that entire first row with the values 8, 6, 4, 2. If I did not have the same number of values as there are in the, well, let me back up for a second. I changed a row. I could have changed a column using a similar kind of notation. But let me instead show what happens if I use a supposed scalar here. That is, this is a one-item vector containing the integer 8. This is then, the same thing happens as what happened up here with these logical indexes. What happens in effect is that R notices that that column has 3 values in it, and so R automatically repeats the 8L that same number of times. So it is as though I had assigned the column 8L, 8L, 8L to the third column. And I get all 3 of those things changed to 8s. Now, if you have, well, okay, so let me do these in the order shown on slide 47 here, rather than getting overly creative. So here's M. Here's M1, row 1, 86A2. Because, okay, it was 8642, and now I've changed the whole third column to 8s. If I say m sub 1 comma gets a vector of 2 values, all right, this is very similar to what we talked about with the logical indexes. There are 4 values in this row. And I have only specified a vector of 2 values to replace that row. Now, R notices the discrepancy, and because 4 is evenly divisible by 2, R automatically just doubles those 2 values into a repeating sequence of 4 total values. And so M now contains 3131. All right? So as long as the value that you're assigning is an even divisor of the length of the thing you're assigning to, you're all set. But if it's not an even divisor, then you get an error. So in this case, in the second half of slide 47 here, what I'm saying is I want to change the third column. Okay, the third column currently contains 388. But I'm saying change that third column using a vector of two values, 8L, keep typing that star, 8L, 6L, and 2 is not an even divisor of 3. So we can't repeat this vector of 2 multiple times to fill in those 3 values, and I get yelled at. I didn't bother to show the error message on my slide because it just, took up space. I get yelled at, and in fact, nothing has changed. So if I look at M, I will see that that third column has not been affected at all by this erroneous assignment that I tried to do. Okay. All right, so we've looked at how to access individual cells. We've looked at how to access rows. We've looked at how to access columns. We've looked at how to access submatrices, that is, two-dimensional submatrices within this overall matrix. And we've also talked about how to modify those values in individual cells or rows or columns. One thing I want to warn you about is that if you assign a value into one of the cells in the matrix that doesn't have the same data type as all the values that are currently there, this will have the effect of changing the data type of every single cell in the matrix to match the data type of the new value that we've inserted. So if I say M sub 1, 1, all right, currently the value of that is this integer 3. If I say M sub 1, 1 gets 4, and I'm not paying attention here, I intended to change that integer 3 to an integer 4, but I forgot to type my L. Okay, I didn't get complained at. And if I look at M, well, that looks okay. But, in fact, every item in M has now had its data type changed to double. And there's no undo for that. You can't press Control Z to undo that conversion of that whole matrix from integers to double. And what's worse is if you say M sub 1, 1 gets, let's say, the string A, now everything in your whole matrix has been changed to strings from numbers. Okay. So be careful. All right, I want to just review some of the attributes that exist for a matrix. Really, a matrix and a vector are the same thing. It's just that a matrix has a dim dimension attribute added to it. And we're going to discover in just a moment that you can, as an alternative to using the matrix function, you can actually just take a vector and add a dim attribute to it, and poof, that vector now becomes a matrix. All right, so if I ask to see what the attributes are for the matrix M, I get told there's one attribute, which is dim, and the value of the dim vector is 3 and 4. I can access that by using the dim function, which just pulls out that dim vector. And I can access just pieces of that by asking for the number of rows in M, n row, or ncol, number of columns. Okay, so these are various ways that I can access the dimension in rows and columns within a matrix. All right, so here on slide 50, we're showing this business of creating a matrix directly from a vector. Recall that we have this vector v1 from some while ago, containing 6 values, 121, minus 714. These are floating point values, double precision values. I can add a dimension to this vector in a very similar way as how I can add names to the vector. That is, I say dim of v1 gets, and then some vector describing the dimensions. There's 6 values in here, so basically I've only got 4 choices. I can create a matrix of 1 row and 6 columns, or 2 rows and 3 columns, 3 rows and 2 columns, 6 rows and 1 column. So let me create a 2 by 3 matrix. All right. V1 is now magically a matrix. It's no longer a vector. Okay. Well, so we've now looked at vectors, which are one-dimensional things that contain values that are the same type. We've looked at lists, which are one-dimensional things whose values are of different types, and whose values are frequently vectors, but could be lists or other kinds of things. We've looked at a matrix, which is a two-dimensional variation on a vector. All of the items in the matrix have to be the same data type. And so now we're ready to take a look finally at the data frame, which is a list of vectors with certain constraints imposed on it. One of these constraints is that each vector in the data frame has to be the same length. All right, so you may recall when we created our list N2 that this was a list that had 2 vectors. The first vector had 5 items in it. The second vector had 2 items in it. So N2 could not be used as a data frame because the lengths of those vectors are not the same. Another constraint is that a data frame has to have a class attribute, and the value of that class attribute has to be the string data.frame. Functions that you pass data frames into will check that class to make sure that it is data.frame in order to figure out what to do with this thing that you've passed in as an argument. We also have a names attribute which lists and vectors and matrices have as well, but in this case names is going to give you the names of the columns, whereas a separate attribute, row names, row.names, is the vector of row names. Those will be created for you automatically by default if you don't specify column names or row names. You'll just get made up column names. And row names, well, I say made up, they're just going to be sequential integer values. Let us imagine that we have some data for a medical practice, and in particular what we have are the age, the height, and the sex for 5 patients. So we'd better hope that our practice actually has more than 5 patients if we're going to survive. Maybe this is just people in a single family, and I'm not going to type these in manually. Let me copy and paste these guys because I'm much too lazy. So I'll copy the vector of ages and the vector of heights and the vector of the sexes of these patients. All right, so now I have 3 vectors. I have one vector of integers, for age. I have another vector of double values for height, and a third vector of character string values for the sex of each of the patients. And of course I can confirm that by using type of. So type of age is integer, type of height is double, and type of SX is character. And here's how I create a data frame. Okay, it's very much like creating a list, except that I give vectors as the elements that are going to go into this data frame. Those vectors become the columns of the data frame. So PATS is short for patients. I'm too impatient to type patients all the way out. All right, so PATS is going to be a data frame with age as the first column, height as the second column, and SX, sex is the third column. That's it. PATS is now a data frame. The column names are taken from the variable names used for the vectors themselves. So the first column is age, the second column is height, the third column is sex, and the row names by default are just going to be 1 through however many items there are in each of these vectors. It is necessary that each of the vectors be the same length, otherwise I would get an error when I did this. Okay. If I ask for the attributes of the PATS data frame, all right, well, it has the attributes that I claimed it needed. Class here, we can see, is the string data frame. The data frame function automatically made sure that that was the case. The names are the column names, and as we can see, those are the names of the vectors. And the row names here are just the sequence of integer values, 1 through 5. Stir of PATS will both give me a little more information and also give it to me in a more compact format. All right, I get told that this thing is a data frame. It has 5 observations of 3 variables. All right, so data frames are intended for doing statistical analyses. Therefore, the assumption of a data frame is that each row is an observation and each column is a variable, a random variable of some kind. All right, so our 3 random variables here are age, height, and sex, and the observations for each of those are 7, 22, 54, 12, 65 for the age, which is an integer, 50, 68, etc. for the height in inches. That's a numeric value, which internally means a double precision floating point. Notice what happens here for the sex vector. We typed in strings, either the string little m or the string little f, but data frames are not happy using strings for categorical values. What the data frame does is to turn these strings into what's called a factor, and each of the possible values is referred to as a level. Now there isn't really any I don't know, level is not really such a, maybe that should be called categories, because they're not ranked. You know, they're not ranked 1, 2, 3, 4, 5. They're just labeled 1, 2, 3, 4, 5. So in our case, we have 2 possible values, 2 categories, 2 levels, and by default, these just get sorted alphabetically. So F here is the first level or category, and that has value 2 associated with it. I'm sorry, that has value 1 associated with it, and m has value 2 associated with it. And if we look at our original data, let me pull that back onto our screen here. Okay, we saw that the vector here was mf, mmf. So that's 2, 1, 2, 2, 1. And that's what we see when we look back at the output produced by stir of the PATS object. We can ask for the class of PATS, which had better be data frame. We can ask for the names of PATS, which is the column names. And we can ask for the row dot names of PATS, which is the row names. We can also, as though data frame were a matrix, ask for the number of columns in PATS, the number of rows in PATS, whoops, not naps, PATS, or for the dim of PATS, which will give us the number of rows and columns. Now, interesting, I have a typo on my slide here. I guess I was a little too lazy when I was typing this in. So 3.5 should be 5.3 because obviously there are 5 rows, 5 observations, and 3 columns, 3 variables. You can establish row names or change row names, or you can change column names as well of a data frame by assigning a value to the row names attribute of the data frame. So rather than these integer values 1 through 5, let me give actual people's names to these rows. These are, after all, people with names, so let's assume that the first row is someone named Al, and the second row is Bell, and the third row is Cy, and then we've got Don and Ellie. All right, now someone's going to complain at me about how I spelled Ellie there, but that is how my mother spells Ellie, so there. Okay, and so now PATS has Al, Bell, Cy, Don, and Ellie as the row names for the data frame rather than just the default integer values 1 through 5. All right, now I mentioned the business of factors that the sex column, male and female, was modified to. This is a collection type, a data structure in Python, and what it is a vector of predefined values. For those of you that have some experience with Python, you can think of this as being like a frozen set. It's a set of fixed values, or a cont set if you're using if you're familiar with C++. And basically what it does is to allow you to represent strings, categories, as small integer values instead. All right, here I have a rather long-winded example of a factor being explicitly created. And when I created the data frame using that vector of strings as one of the columns, the data frame creation function did this internally. All right, so F now is a factor with levels F and M, and when I display them as a factor, they display as M or F, but actually the type of these things is integer. F for 1 for F and 2 for M internally. I can show that by Well, I can access an individual item on the factor. The factor is a vector, and I can access, for example, the first item from the factor f by saying f sub 1. I get back an m, and I'm told, okay, there are two possible levels or two possible categories for this factor, f or m, and it happens that as an integer, the factor value for m is 2. All right. Now, one of the things that we talked about when we introduced data frames is that the data frame has to have a class associated with it called data.frame. Many things in Python have a class associated with them, and this is how Python somewhat awkwardly represents an object-oriented notion of classes. A class is simply an attribute of an object, and then those classes can be used by functions that are called that examine those classes. So the class of Pats is data.frame. If I have a list like n, and I ask for the class of that list, I get told, okay, that's a list. If I ask for the class of m, I get told, okay, that thing is a matrix. In addition to the class, you'll also read about something called the mode of an object as well. And the mode you can sort of think of as how you're allowed to use the thing. The data frame Pats is of class data frame, but its mode is list. And what that means is that any operations that you can do on a list, you can do on a data frame. So I can say things like Pats sub 1 to get the first column from Pats. All right, Pats is a list of columns, and Pats sub 1 is the first column. Pats sub 2 is the second column. I can use Pats sub age to get the age column, or I can use Pats $age to get the age column. So in other words, because the mode of Pats is list, that means operations that I can perform on lists, I can also perform on data frames. The type of Pats also is list. And you can think of the type of as being the low-level implementation details of the thing. I am not going to oblige you to know the clear distinction between classes, modes, and types. R is fairly peculiar in having these three different ways of... I mean, most languages have data types. And also classes. The concepts of class and type are typically just interchangeable and really historical. For example, in the C language, int is a data type, but you can also think of int as a class, and it doesn't really change your concept of what's going on with an int. But in R, these are three different, conceptually different kinds of things. If I create a matrix, I actually have this matrix M sitting around. Oh, I wrecked M by converting it all to strings. So let me create a new matrix M2 by copying and pasting this code here. Now that I think about it, that must be why I wrote this example. Okay. Okay, so M2 is now a matrix containing the same values that that old M back from slide 41 contained, and its class is matrix, but its mode is numeric. That is, I can do numerical computations using this matrix. I can do things like multiplying it by a quote scalar unquote, which of course is actually a vector that gets expanded to the same size as the matrix, and its type, which is the low-level implementation of this thing, is integer. So here we have an object M2 whose class and mode and type are different from each other, okay? All right. Okay, so a data frame is a list, as I said. Its mode is list, and its type, in fact, is list. That means anything you can do with a list, you can also do with a data frame. And I already showed you these examples here. I can use the double subscript notation to access one of the columns. I can use the dollar symbol and the column name to access a column, or I can use the double subscript with the name of the column to access a particular column. But in addition to these access capabilities that a list provides, I can also use additional matrix-like access capabilities that the data frame logic adds. So recall that for a matrix, I could say row comma column. And likewise, I can do that same thing for a data frame. So row 1, column 3 is going to be Al's gender, M. Row Bell, column height, is going to be Bell's height. Row 2, all columns, is the entire observation about Bell, whereas Pat sub comma age is all of the ages of all of the observations. Okay, so a data frame is a list, but of a specific kind with certain constraints and also with additional access functionality that you don't have with ordinary lists. Okay, so we've pretty well flogged vectors, lists, matrices, and data frames. And that gets us to the end of the week 2 materials. All right, well, I hope you're all well. I hope you're all taking care of yourselves. And I will post a homework exercise soon. And also, in the next day or so, produce another video talking about the group projects that you'll need to do for the course. Okay, so take care.